Okay, so the other technique we're going to talk about is the Thévenin equivalent circuit. And what the Thévenin equivalent circuit does is it allows us to simplify a larger circuit network down to something relatively simple. So if we have a circuit, and I'm just going to draw it as a box. So we have, and I typically call this the circuit network. So this consists of our voltage sources, our current sources, our resistors, all the things that we have in circuits. And if we can isolate one element, which I'm going to call the load, okay? So one element, and we isolate it by two nodes, okay? So this could be, say, I'll draw it in blue, a resistor, okay? Connected at 2 points. So what we can say with the Thévenin equivalent circuit is that we can take this part, the circuit network, okay, and we can make this circuit network into its Thévenin equivalent circuit, which consists of a single independent voltage source in series with a single resistor. We call the resistor the Thévenin equivalent resistance. We call the voltage source the Thévenin equivalent voltage source, so RTH and VTH respectively. And then we can connect that load back to those same 2 points. And the voltage and current associated with this load will be the same. So if we call this VL or we call this IL, that same voltage and current would have been reflected with the entire circuit network attached, will also be reflected on its equivalent version. Okay? Now, this may seem complicated, and actually Thévenin's theorem is hundreds of pages long. We're not going to go through that, obviously, but it may take you a couple of times doing this before you get comfortable with it. So let's go through the steps, and we're going to do the steps pictorially. I think it's easier to look at it from a diagram as much as it is the words. So Thévenin, and now I can say Thév equivalent circuit steps. Okay, so what we're going to do in step 1 is we are going to identify the circuit network versus the load. Okay, so again, just drawing kind of boxes here. We have to be able to clearly identify between our circuit network and the load. Okay, so a load can actually be a group of elements together, but in this class, it's going to be a single element. A resistor 99% of the time. Okay, so we need to now, step 2, we need to separate them. So we're going to separate the circuit network and the load. Okay, so we're just going to break them apart at the node which connects them, the nodes which connect them. So we'll have our circuit network with a set of open terminals, and then our load with its set of open terminals. Okay, so then step 3, and this is, we're going to focus all on the circuit network from here on out until the very end. So we're going to find what we call the open circuit voltage. Okay, and it's called the open circuit voltage because we're finding it across the terminals that we've just opened from the previous step. Okay, so we're going to take our circuit network, okay, so there's our circuit network, and these terminals that we just opened, we are going to label a voltage VOC, the open circuit voltage. So it's the voltage that exists across these open terminals. Okay, and we can find this open circuit voltage using any method that we like. Okay, so we will find VOC using any method. So depending on how complex the circuit is, you might use voltage division or current division. You might use a very simple nodal or mesh equation. It might be more complicated. You might use superposition. There's that's going to be up to you. So you're going to get to choose how you do that. Okay, but note that this circuit network here is different than our original circuit. Okay. Okay, so once you find the open circuit voltage, we set the Thévenin equivalent voltage source to that open circuit voltage. Okay. Now, oftentimes I get questions about the relative polarity of the open circuit voltage. And what's important here is to remember that whatever the node is, or the terminal where the plus sign of your voltage is versus the minus sign of your voltage, is reflected back on the load. So for example, I would call where these two elements were connected points A and B, for example. Okay, and so this would be A here, this would be B here. And so when we draw our circuit, we would want our source and our resistor to still be relative to A and B. And we'll see that as we move along. Okay, so step 4. We're going to find our Thévenin. So step 3, we found the Thévenin equivalent voltage source by finding the open circuit voltage. Step 4, we're going to find the Thévenin equivalent resistance. And there's 2 methods, okay? There's method A, which is the quick method. And there's method B, which is the long method. I'm quite creative. So the quick method, so method A, quick method may be used for circuit networks with only independent voltage sources. Okay, so when you look at your circuit network, if it only has independent sources in it, 0 dependent sources in it, then we can use the quick method. Okay, and so the quick method, we are going to turn off all the independent sources, and they're going to be the only sources in the circuit, but they're all going to be independent. So turn off all independent sources. Okay. Remember, there are no dependent sources. Okay, and why do we do this? Because we don't know how to turn off dependent sources. So that comes from those examples that we worked on superposition, okay, on the example part of the module. So we can't turn off dependent sources. So right for the quick method, we have to have only independent sources, and we're going to turn them all off. And so what we're going to be left with is only the resistors. Okay, and so then we will have our circuit network here. So circuit network, sources off. Okay, and then what we're going to find is relative to these 2 points, we're going to find the equivalent resistance. And we'll do that by making series and parallel combinations as required. Sometimes it's as simple as looking at it and saying, oh, there's only 1 resistor, or there's only 2 resistors. And so it's very easy to look at and get. Sometimes it may take a little bit longer to do that. All right. But whatever that equivalent resistance is our Thévenin equivalent resistance. Okay. And that's for the quick method. The long method. So for the long method, we are going to take the circuit network that we've already found the open circuit voltage for. Okay, source is all on. All right. And then we are going to short those terminals together. Okay, and we're going to find the short circuit current. So ISC is equal to the short circuit current. And notice that the short circuit current, again, putting in these A and B designations here, the short circuit current always flows from plus to minus with respect to the way we labeled the open circuit voltage polarity. Okay? So, and you'll solve for that short circuit current using any method that you like. Okay? Notice the load is still disconnected. We're only looking at the circuit network. All right? And then we can find the Thévenin equivalent resistance now, our Thévenin, as being equal to the open circuit voltage divided by the short circuit current. Okay? So, some things to note here, that for the circuits that we will work in this class, our Thévenin is always going to be a positive quantity, which means that V open circuit and I short circuit both have to have the same sign in order for our Thévenin to be positive. So keep that in mind. Now, it's possible outside of this class that you could get a negative resistance. Remember, this is just an equivalent model of what's going on, and it's possible to have a circuit that is not well behaved when it comes to resistances, and so you could end up with a negative resistor, but not in this class. Okay, I won't give you a problem like that. All right, so once you have found the Thévenin equivalent voltage source and the Thévenin equivalent resistance, then we're going to go to step 5. And step 5 is to build your equivalent circuit and add your load. So our Thévenin equivalent circuit is going to consist of our Thévenin equivalent voltage source, our Thévenin equivalent resistance, and then our load gets reconnected at the same 2 points. And then we're going to solve for the voltage drop across the load or the current flowing through the load. And this is just going to be either voltage division or an Ohm's law equation. Okay, that's all the steps for a Thévenin equivalent circuit problem. So let's do a simple one to start. Now your load can exist anywhere in the circuit. We're going to start with one that's on the end of the circuit, but it doesn't always have to be there. Okay, and I'm just gonna, give me a second, I'm gonna grab this and move it over a little bit. Okay, so this is a 10 volt source, this is a 5 ohm resistor, this is a 4 amp source, 1 ohm resistor, 2 ohm resistor, 8 volt source, 4 ohm resistor. And what we want ultimately is to solve for that voltage VO across that 4 ohm resistor. Okay, and we're going to do that by finding the Thévenin equivalent circuit of the circuit network, reconnecting the load, and then solving for V0. Okay, So step one is to identify the circuit network relative to the load, okay? And since this is what we're trying to solve for, the voltage VO across that 4 ohm resistor, that 4 ohm resistor is going to be our load, and everything else is going to be our circuit network, okay? So I'm going to draw this out separately, but I won't do this for all the problems after this. Okay, so we'll have our 10 volt source, our 5 ohm resistor, our 1 ohm resistor, our current source 4 amps, our 2 ohm resistor, and our 8 volt source, and here's our 4 ohm load. Okay, so this is our circuit network. And this is our load. Okay, and again, your load is going to be the element for which you are solving a voltage or current for. Okay, so I'm just going to grab this and copy it. You will, of course, want to draw it again. Okay, so, and I'll give you a minute or two to do that, or you can pause the video, probably would be best. So here's our circuit network, and we want to solve for the open circuit voltage across the terminals. Okay, so this is going to be VOC, the open circuit voltage across those two terminals that we have just opened. So notice this is a different circuit than what we started with. So I don't want you to feel like somehow this 4 ohm resistor still has to stay in there. Remember, we're removing the load. Okay, so we're solving for a different circuit right now, or we're evaluating a different circuit right now. And before we get all excited about it, about jumping in and thinking, oh, I've got to do mesh, I've got to do nodal, I've got to do some sort of simplification, let's sit back and look at what we actually have to solve for. Okay, so we're solving the voltage from here to here, okay, which means we need this voltage VOC. If we look at this loop here, and while this is an open loop, we can still, the KVL equation still has to work here. So if we knew the voltage drop across every one of these elements, and we know this voltage here across these two terminals, they would have to sum together to be 0. Okay, we know the voltage here because it's the value of a source. We don't know the voltage across the 2 ohm resistor. So we have to figure out what that is. Okay, so once we know the voltage drop, say let's label it like this, just with the highlighter for a second, then we know this voltage, we know this voltage, we know this voltage, and we can write that KVL equation. Okay, so how do we go about finding this voltage? So let's look again and see what we know in the circuit before we jump headlong into writing nodal equations or mesh equations. So this current source here, where is it going to flow? Okay, so it's got to flow through the 2 ohm resistor for sure, but does any current flow in this direction through the 8 volt source? Hopefully you're saying no, none of it's going to flow through the 8 volt source because there's an open circuit here. So no current's going to flow here. You can still have a voltage, but there's no current flow because of the open circuit situation. So we know that all of the 4 amps of current is going to flow through this 2 ohm resistor and then come back to the rest of this circuit. Okay, so that makes this quite simple, right? Because we can label this voltage and we'll call it V sub R. And we know by Ohm's law that V sub R is going to be 4 times 2 or 8 volts. Okay, fantastic, right? So again, Now the circuit's very easy to solve. We didn't have to write a single nodal equation. We won't have to write a mesh equation. We will have to write a simple KVL equation. All right, and so we're going to do that. We're going to write a KVL equation around this loop. I'm going to call it loop 1. Now it's an open loop, but it's still a loop, and KVL still has to be satisfied. So by KVL around loop 1, starting with VR, moving from minus to plus, I'll add VR. Coming around to the 8-volt source, moving from minus to plus again, I'll add 8. And coming around to this open circuit voltage here, so I've gone from VR to the 8-volt, and now I'm going through this. I know what the voltage drop is across there. It's our open circuit voltage. I'll be moving from from plus to minus, so I'll be subtracting that voltage, VOC. I'll be back to where I started. I can sum to 0. And so when I solve this and substitute in that VR is equal to 8 volts, I will get that VOC is equal to 16 volts, which means that my Thévenin equivalent voltage source is going to be 16 volts as well. Okay? All right, so the next step is to find that Thévenin equivalent resistance. And what we want to do, if you recall, is look at the circuit network and see if there are any dependent sources. And there are none here, which is great news for us because we can use the quick method, which is a lot simpler. So remember, for the quick method, we are going to turn off all of the sources, and we're going to turn them off just like we did for superposition. But in this case, we're turning them all off. We're not leaving one on. So we're going to turn off the voltage source, the 10-volt source, by replacing it with a short circuit. Then we'll have the 5 ohm resistor. We'll have the 1 ohm resistor. The 4 amp source we are going to open up. And I'm going to go ahead and show those terminals here to start with. Then we have our 2 ohm resistor. And our 8-volt source, again, is going to be shorted. And so this is what we're left with. Again, we have shorted the 10-volt source. We have shorted the 8-volt source, and we have opened the 4 amp current source. So all sources are off. All right, and so now we have our 5 ohm resistor, our 1 ohm resistor, and our 2 ohm resistor. And what we want to do is we want to find the equivalent resistance looking into these 2 points, so relative to this point and this point, okay? We don't want to do anything to lose those 2 nodes. And those 2 nodes come back to here and then this common node across the bottom. So the question is, which of these resistors will become part of that Thévenin equivalent resistor? Okay. So let's talk for just a second about how a voltmeter or an ohm meter, something that measures resistance, works. So I'm just going to draw a little circuit here, or a little box here. So we have if you've ever seen an ohm meter, a fluke, for example, there's a big dial here that points to different display mechanisms for whether you're doing current, voltage, or resistance. And there'll be a big display here. And there's a couple of places where we're going to connect probes to. And one of them is going to be, or 2 of them are going to be for resistance. Okay, and we're going to connect one probe to one part and one probe to another part where we're taking that equivalent resistance measurement. All right, and so what an ohm meter does is it sends out a test current. Okay, so it sends out a test current, and then it reads a voltage internally based on that test current. So this test current, in order for a resistor in this circuit here, in order for a resistor in this network to affect the equivalent resistance, current has to be able to get to it. So if we look at this test current, it can flow here, and then its only choice is to flow down here and then back out. Okay, it can't go this way and then come back because current can't flow back on itself. Okay, so for this particular circuit, the 5 ohm and the 1 ohm resistors are not affecting our equivalent resistance. All right, only the 2 ohm resistor is. So our Thévenin equivalent resistance, or our equivalent resistance here, is just the 2 ohm resistor, or our Thévenin equivalent resistor in our equivalent circuit is 2 ohms as well. Okay. All right, so now let's draw our Thevenin equivalent circuit. It consists of that 16 volt Thevenin equivalent voltage source, our 2 ohm Thevenin equivalent resistor. We're going to reconnect that 4 ohm load. And we're going to solve for the voltage drop across that load with that polarity VO. And by voltage division, VO is equal to the total source voltage available to us, 16, multiplied by the resistor we want to know about, divided by the series combination of all the resistors, in this case 4, divided by 2 plus 4. And so this is going to be 10.67 volts. Okay? So with our Thevenin equivalent circuit, we found the open circuit voltage, we found the Thevenin equivalent resistance, we were able to solve for that voltage VO. If we went back to this original circuit here and did nodal analysis or mesh analysis to solve VO, we would have gotten the same answer, or superposition for that matter. All right, let's do another example. Now that we've seen the method in action here. All right, so we are going to have and I'm going to pull this circuit down a little bit because I'm way at the top of the page. There we go. All right, so this is an 8 ohm resistor. This is a 5 amp source. This is a 10 volt source. This is a 2 ohm resistor. This is a 3 ohm resistor. This is a 4 volt source. And this is a 5 ohm resistor. And we're going to solve for the current flowing through this resistor, Ix, using a Thevenin equivalent circuit. And so since this is our our load, excuse me, what we're trying to solve for here, trying to solve for the current through the 5 ohm resistor, this is going to be our load. All right, so what I want to do is kind of show you here, because this is in the middle of the circuit, sometimes that can be a little confusing. What we're doing here is, and I'm going to use a different color, I'll use green here, is we're basically saying, so if you think about taking this part of the circuit, this network part, and kind of folding it back into the page, okay? And then what we want to do is we want to find, and I'm going to draw it way out here. That was ridiculously large. Let's try that again. There we go. So here's our Thevenin equivalent voltage, our Thevenin equivalent resistor here. And so basically what we're saying is, if this is, remember I had that A and B around our load, okay, we are looking at the Thevenin equivalent circuit relative to those 2 points. And so we're taking this entire circuit network and resolving it as this equivalent model of a voltage source and a equivalent resistor connected at the same 2 points. Okay, and so you can see the voltage source of our Thevenin equivalent voltage source. The plus is going to be up here at A, and the minus is going to be down here at B. And so so that can help you maybe keep track of things here a little bit easier. Okay, so since the 5 ohm resistor is going to be our load, that's what we have to pull out when we draw the circuit network. So we're going to have the 4 volt source, the 3 ohm resistor. We're going to take out that 5 ohm resistor, although it will be important here to leave those terminals in place so we can see, because we have to measure a voltage there later. So I've taken out the 5 ohm resistor because that's our load. Here is the 5 amp source, the 2 ohm resistor, the 10 volt source, and then our 8 ohm resistor. Okay, so here's the circuit network. We've taken the load out, all right, and now we have to find that open circuit voltage across those two terminals. And I always say you want to hang on to those terminals to make sure you don't lose where we're taking our new measurement, solving for our open circuit voltage. Okay, and remember that you can solve for this using any method that you like. Okay, so I did nodal analysis here. Yeah. Okay, so and this is how I did it. So I grounded this bottom node, and I'm going to highlight the nodes here. So I've got a node down here at the bottom. Okay, I've got a node here, and then I've got this node here. Okay, so I'm gonna ground this bottom node. This will be our reference node. I'm going to call this node voltage here V1 and this one here V2. Okay, and because we have this 10 volt source now that is isolated between the node here at V2 and our reference node, we know something about that node voltage, right? So 10, the value of that source, has to equal plus 0 minus V2. So V2 is equal to minus 10 volts. So this is what we know before we get started. We also know what VOC is equal to as far as an expression is concerned. VOC is equal to V1, or plus V1 minus 0. Okay, so we know these two things before we get started. Since we know what V2 is, we only have to write that node 1 equation. So node 1 equation is going to be, we've got 3 connections here, so we're going to have the current flowing to the left is going to be V1 minus 4 over 3. The current flowing up is going to be V1 minus V2 over 8, plus the current flowing to the right is going to be 5. Okay, and then we'll sum to 0. Now, there is no current flowing here, right? This is an open circuit, so we only have to worry about these 3 currents. So V2, if you'll recall, remember that V2 is equal to minus 10 volts. So when we substitute in minus 10 into V2 and solve, we will get that V1 is equal to minus 10.72 volts, which means that the open circuit voltage is equal to minus 10.72 volts. Which means that our Thévenin equivalent voltage source is going to be minus 10.72 volts. Is it a problem for the Thévenin equivalent voltage source to be negative? Absolutely not. It absolutely can be negative. Okay, so our next step is to find the Thévenin equivalent resistance. Okay, so we're going to draw the circuit network again, but we're going to shut all of the sources off. All right, so we will have, so we're going to find our Thévenin now. So we will have a short circuit where the 4 volt source is. We'll have our 3 ohm resistor. Here's where our load was. We want to hang on to these terminals because this is where we're taking our equivalent resistor measurement at. We're going to have an open circuit where the current source is. Okay, so here's our 2 ohm resistor. And it is also going to be shorted by turning off the 10 volt source. All right, and then we're going to have the 8 ohm resistor connected back to here. All right, so this is 3 ohms, this is 2 ohms, and this is 8 ohms. And we are finding the equivalent resistance relative to these 2 points in the circuit. So we don't want to do any simplification that will jeopardize either of those 2 nodes. Sorry. Okay, now we've already said that this, or I've hinted at least, that this short here, that the voltage source has shorted out this resistor. Okay, so no current, if we're going to do that measurement, send out that test current, no current is going to choose to flow through this 2 ohm resistor when it has a nice short circuit it can flow through. Instead, current takes the path of least resistance. In the case of a short circuit, the current only takes the path of least resistance. Okay, so we don't even have to draw that. So we could go ahead and erase this, and I'm going to go ahead and do that because we don't need it in here. And so what I would suggest that you do is draw it at first, and then when you notice something like that, erase it off or redraw the circuit. All right, so now, what is our equivalent resistance going to be? Well, we've got this 3 ohm resistor connected between here and here, and we've got the 8 ohm resistor connected on the other side. So those 2 elements are going to be in parallel because they share the same 2 nodes. If we combined 3 and 8 in series, we would lose one of these nodes, which means we wouldn't be taking our measurement correctly. All right, so REQ is equal to 3 in parallel with 8. That is going to be 2.18 ohms. Product over sum 24 divided by 11. Okay, so now we have our Thévenin equivalent circuit. We have our voltage source, V Thévenin, and our resistor, R Thévenin. V Thévenin was equal to minus 10.72 volts. R Thévenin was 2.18 ohms. We're going to reconnect the 5 ohm resistor. 5 ohm resistor. And we're going to solve for this current flowing through that 5 ohm resistor. All right, and this is just going to be an Ohm's law equation. Ix is equal to minus 10.72 divided by the series combination of the 2 resistors. The passive sign convention is holding. Passive sign convention is holding, so this current's flowing from minus to plus through the source, and then will flow from plus to minus through the resistor. It just so happens that our source is negative here, but that's okay. We're going to end up with a negative current, which is going to balance everything out nicely. This is going to be minus 1.44 amps. And again, if you went back to the original circuit and solved for this current Ix using mesh or nodal or superposition, you're going to get that same answer. And I would encourage you to do so, especially superposition, since you're still learning that whole technique right now. Okay. So what happens if you have a circuit network with dependent sources in it? We're going to talk about those in the example, the examples that we're going to work in the example module, or example part of the module. So we'll work those next.